Thank you, Ryan, for the introduction. So hello, everybody. I'm Priyanka. So today I'll be talking about efficient algorithms for synthesizing Tcount and Tdepth optimal circuits. And this talk is based on two of my papers, which have been co-authored with Michele Moshka and Vlad Gargi. So this is the rough overview of my talk today. First, I'll introduce the problems, give some essential preliminaries, and then I'll describe channel representation of unitaries. After that, I'll describe two provable algorithms and two heuristic algorithms. So first, let us understand what's a quantum circuit synthesis algorithm. The input of a quantum circuit synthesis algorithm is a unitary, which is of size n cross n, where n is 2 to the power small n, where n is the number of qubits. So it is exponential in the number of qubits. And the output is the decomposition of this unitary into a sequence of gates, which usually belong to a universal set. And in resource optimal synthesis problems, there is a further constraint on the output that we have to optimize the number of certain resources, for example, the T gates. Now here, I would like to briefly point out what are resynthesis algorithms. In a resynthesis algorithm, the input is a circuit and the output is also a circuit, and the task is to reduce the number of these resources like T gates. So now a circuit can be obtained from unitary can be obtained from a circuit by using any synthesis algorithm. But most resynthesis algorithms, if not all, they do not account for the complexity of this step, and that is why they have much better complexity at the cost of optimality of the results. This talk is only about synthesis algorithms, and I will not delve into resynthesis algorithms or the differences and pros and cons of these two kinds of algorithms further. Now, suppose U dash is the unitary implemented by the gates which are obtained in the decomposition. That is, U dash is the product of these gates in the decomposition obtained from the synthesis algorithm. Now, depending upon U dash, there can be two kinds of synthesis algorithms. In approximate synthesis algorithm, U dash is not equal to U, but the distance between U dash and U is at most some epsilon, which is strictly greater than 0. And in exact synthesis algorithm, U dash is equal to U up to some global phase. This talk is about unitaries, which can be exactly implemented by the Clifford plus T gate set. And there has been some nice result by Giles and Selinger, which throws some light upon the structure of these unitaries. For example, each of their entries, they belong to this ring, Zi 1 by root 2. This Z is the ring of integers. At most, one ancilla is sufficient to implement these unitaries. And if the determinant satisfies certain criteria, then no ancilla is required. Now, a quick recap of some terms. I know most of you might know all these things. What is a universal gate set? It is a set by which it is possible to approximate any unitary operation to arbitrary accuracy by a quantum circuit, which has these gates. For example, the Clifford plus T is a very popular universal gate set. The Clifford plus T operators, they belong to the group which is generated by the Hadamard gate, the T gate, and the C naught gate. The n-qubit Clifford operators, which is a subset of this group, they belong to the group which is generated by the Hadamard gate, the phase gate, and the C naught gate. Apart from being a universal gate set, these Clifford plus T operators, they also form a fault-tolerant gate set. That is, they have a fault-tolerant design in most error correction schemes. And this is required to deal with errors due to noise on quantum information, quantum gates, state preparation, measurements, etc. This becomes very significant for long computations as the error builds up and the output becomes unreliable and hence useless. Now, the Clifford group gates, they have a transversal implementation in most fault-tolerant schemes. For example, this is the transversal implementation of a C0 gate between two logical qubits which have been encoded with the Steen code. And this operation is less costly. On the other hand, the non-Clifford gates like the T gates, they require large ancilla factories, additional operations like gate teleportation, state distillation, etc. These are less accurate procedures, they require more time and space, and hence they are more costly to implement. Thus, it is important to reduce the number of T gates or the T count. It has been shown by Fowler that a fault-tolerant circuit's runtime is directly proportional to its T depth. So it is also important to reduce T depth. Now I'll define what is the T count and T depth of a circuit and a unitary. For a circuit, the T count is the number of T gates in it. And the T depth is the number of stages where the T or T dagger gates, they act in parallel. For example, this is the circuit of a Toffoli gate, which has whose T count is 7 and the T depth is 3. Now, there can be more than one circuits which implements the same unitary. So the T count of a unitary is the minimum number of T gates in a Clifford plus T circuit that implements it. And the T depth, or we call mean T depth, just to avoid some confusion, is the minimum T depth of a Clifford plus T circuit that implements it. And these quantities may change with the use of, say, additional ancilla qubits or measurements with classically controlled operations, etc. Now, in this talk, I'll describe algorithms for two problems. In the first problem, which is mean T-synth, the task is to compute a T-count optimal Clifford plus T circuit for an exactly implementable unitary U. A variant of this problem is count T, where we have to determine the T count of this unitary, and in the decision version, we have to decide if the T count is at most some positive integer m. It has been proved by Goset, Klosnikov, Mosca, and Russo that if we can solve count T, then we can synthesize a T count optimal circuit for the unitary with some overhead, which is polynomial in the T count of U and the dimension of U. In the second problem, mean T depth, the task is to compute a T depth optimal Clifford plus T circuit for U. And in the decision version, we have to decide if the T depth of this unitary is at most some positive integer D. Okay, now I'll tell you about some previous results. Like these were the best state of the art before our work. I'll talk about only a few papers. So for synthesizing T count optimal circuits, the meet in the middle technique was introduced by Goset, Klosnikov, Mosca, and Russo, GKMR, for this problem count T with space and time complexity order n to the power tau U. Okay, so this is like the exponent. It is exponential in the T count of U, and the base is capital N, which is itself exponential in the number of qubits. This technique had been parallelized by Di Matteo and Mosca with deterministic walks, but the algorithm suffers from that same asymptotic complexity. I mean, that same dependence of T count in the exponent. This same MITM technique was used by Amy, Mashlov, Mosca, and Rotteler for synthesizing T-depth optimal circuits with space and time complexity 2 to the power k n squared to the power the T-depth of U. So here, the small n is the number of qubits. So in our papers, we improved the complexity of both these problems significantly. So in the first paper, which has been co-authored with Michele Mosca, we gave algorithms for synthesizing T-count optimal circuits. So in the rest of my slides, most of the contents which related to T-count has been taken from this paper. In the second paper, which has been co-authored with Vlad Kargiu and Michele Mosca, we design algorithms for synthesizing T-depth optimal circuits. So in the rest of the talk, most of the contents related to T-depth have been taken from this paper. In all our algorithms, we use channel representation of unitaries. So first, let me describe what is the channel representation of a unitary. So for an n cross n unitary, the channel representation is an n square cross n square matrix with rows and columns which are indexed by n qubit Paulis. So the RSS entry is given by this term, trace of PRU PSU dagger multiplied by this constant 1 by 2 to the power n. This is derived from the fact that the n-qubit Pauli operators, they form a basis for the space of all Hermitian matrices. For a unitary, its channel representation is a unitary itself. It respects the multiplicative property, the tensor product property, and each of its entries is real. So if U is exactly synthesizable, so we can say that the RSS entry, that each entry of the channel representation belongs to this ring Z1 by root 2. The channel representation of a Clifford operator is very easy to point out. It has exactly one non-zero entry in each row and column, which is equal to plus minus 1. Now, for any element in this ring, the smallest denominator exponent is defined as the smallest natural number, such that this element can be written as a plus b root 2 by root 2 whole to the power k. The SDE of 0 is 0, and for any matrix, the SDE of the matrix is equal to the maximum of SDE of any of its entries. For a Clifford operator, the SDE is 0, and it has been shown by Goset, Klosnikov, Mosca, and Russo that the T count of a unitary is equal to the SDE of its channel representation. Thus, these two concepts are related. Now, if you use exactly synthesizable, then we can, over the Clifford plus T gate set, then we can write Q as an alternative product of Clifford operators and the T or T dagger gate. We can also club together these terms, play with the phases a little bit, and get this compact representation, U as the product of these RPJ terms and C0. Now, each of these RPJ terms has one T gate, that is, it's a T count 1 circuit, and these circuits can be constructed very efficiently. And for R dagger P, it has one T dagger gate. So in the channel representation, since the phase goes away, we can have the channel representation as the product of these RPJ hats, or the channel representation of these RPJs, and the channel representation of a Clifford operator. Now let's look at the structure of these RP units, the channel representation of these RP units. So it has the diagonal elements of these matrices are either 1 or 1 by root 2. And exactly half of these diagonal elements are 1 by root 2. For example, this is the channel representation of our YX. So this is a 16 cross 16 matrix, and exactly 8 of its diagonal elements are 1 by root 2, and 8 others are 1. Now, if a diagonal element is 1, then the rest of the entries in the corresponding row and column is 0. If a diagonal element is 1 by root 2, then there exists exactly one other entry in the corresponding row, which is 1 by root 2, and one other entry in the corresponding column, which is minus 1 by root 2, or vice versa. And the rest of the entries are all 0. For example, so this is the complete structure of the matrix. All those places which I have left empty are actually zeros, which I didn't write just not to mess up with the view. Okay, so here, as we see, there are 8 diagonal elements which are 1 by root 2. We can distinguish these patterns. So for example, in this red square, so if this diagonal element is 1 by root 2, there is one other element in the row which is minus 1 by root 2, and in the corresponding column which is 1 by root 2, and obviously this other corner of the square will be 1 by root 2. So we can have 4 such squares in this matrix, and thus we can represent this matrix by an array of length n square by 4. For example, so we just need to store the pairs of the form j plus minus k, which implies that the j diagonal element is 1 by root 2 and the jk entry is plus minus 1 by root 2. We do not need to store k minus plus j because it will be automatically implied. For example, this whole matrix can be represented by this array of size 4. Each of these entries is a pair. Now, the inverse of these matrices are easy to calculate. Just flip the sign of the off-diagonal elements. Now, what happens if we multiply any unitary with the channel representation of an RP unit? For example, W is the product which is obtained after multiplying V by the channel representation of some RP. Now, if the ith diagonal element of RP hat is 1, then the ith row of W is equal to the ith row of V. If the ith diagonal element is 1 by root 2, suppose the ilth element is 1 by root 2, then what happens? Which this will imply that the lth diagonal element is 1 by root 2 and the lith entry is minus 1 by root 2. Then the ith row of W will be equal to the sum of the ith row of V and the lth row of V multiplied by a constant 1 by root 2. And the lth row of W will be equal to the difference of the lth row of V and the ith row of V multiplied by 1 by root 2. Thus it implies that the STE of W can differ from the STE of V by at most 1. And the complexity of this multiplication operation is order n to the power 4. So in comparison, if you would have used the state-of-the-art fastest matrix multiplication algorithm, for example, the one given by Legal, we would have had a complexity of n to the power 4.75 at least. Now, as I said, that each entry of this channel representation of unitary comes from this ring Z1 by root 2. Thus, we can represent each of these entries by a tuple of 3 integers, a, b, and k. And so we do not need any floating point operation for any of our operations we have done for addition, subtraction, inverse, or multiplication. All our algorithms only use integer arithmetic. Okay, so now I'll describe some provable algorithms for synthesizing Tcount and Tdepth optimal circuits. But before that, I'll describe the concept of Coset label, which is essential for our algorithms. So this sort of acts like a representative for the channel representation of unitaries. It's a matrix valued function that tells us if two unitaries u and v are such that u is equal to v times c for some Clifford c up to some global phase. Okay, so and how is it calculated? First, we rewrite the channel representation such that each non-zero entry has a common denominator, which is equal to √2 times the ST of the channel representation of this unitary. Then for each column, we look at the first non-zero entry such that the denominator is equal to that quantity. And now if a is less than 0, so the numerator is now a plus b √2. Now if a is less than 0 or a is equal to 0 and b is less than 0, we multiply the column by -1. Okay, and then we permute the columns so that they are ordered lexicographically from left to right. It has been shown by Coset, Klossnikov, Mosca, and Rousseau that if the Coset label of the channel representation of two unitaries are equal, then we can write as the u hat is equal to v hat times c hat. That is, this condition is satisfied. U is equal to v times c up to some global phase. Now we can have some sorted Coset database which stores these Coset labels. Okay, so this is a list of all unitaries with Tcount k and having distinct Coset labels. And we always sort this Coset of this database such that they have some kind of an ordering, say ordered according to lexicographically depending upon the Coset labels. Okay, so for our provable algorithm for synthesizing Tcount optimal circuits, we basically modified the MITM technique of GKMR, and we introduced a nested MITM technique. So in this algorithm, the input is a unitary, M is the test Tcount, and C is the level of nesting that we want. And the output is the Tcount of this unitary. If it is less than M, or we return no. Now, the intuition is as follows. We know that the channel representation of this unitary is equal to the product of these RPs and the channel representation of a Clifford. So we search for this set of these RPs such that this condition is satisfied. So we first calculate the channel representation and its Coset label. Then we pre-compute these sorted Coset databases up to Tcount m by c. To compute this database, we first start with identity. Then we multiply all unitaries with Tcount I-1, which is in the database, with RP hat, such that we get this unitary with Tcount I, and we include it in the database if and only if its Coset label is new. We always maintain the order. For example, this is a graphical representation. So we'll see a lot of these trees in our slide. So each node of these trees, they represent one unitary, and these edges represent multiplication operation. Okay, so in this case, the multiplication is by the RP units, and we store all these unitaries because they have new Coset labels. Now we check if the Tcount is at most m by c. We can simply check their databases, whether they have that labels in our database. We can do a binary search because it's ordered. If we find it, then we are fine. Else, we do a nested meet in the middle procedure. This is an iterative procedure where in each iteration, first we check whether the Tcount is twice m by c, then we check if it is thrice m by c, and so on. For example, to check whether it is twice m by c, we start with any unitary which has Tcount m by c, which is already in the database. We calculate v, which is w dagger v hat, which is w dagger hat u hat, and we check if the Tcount of v is at most m by c from the database. If yes, then we say that the Tcount of u is Tcount of v plus m by c. Else, we again check if it is thrice m by c, and so on. For example, suppose this is one unitary with Tcount, in this case 2. And if we calculate now v hat, and we see like W11 is another unitary which has the same Coset label, and then we can say that the Tcount of this unitary is Tcount of W24, that is 2 plus W11, which is 1, so 3. And if we do not find any such label after all these iterations, then we say that the Tcount is more than m. So for c is equal to 2, this is basically the MITM technique of GKMR. Now, this is a comparison between the complexity of our algorithm with GKMR. We see like we have a reduced space complexity at the cost of some increased time complexity. But this gives a time-space trade-off for MITM techniques when used in these kinds of algorithms. Now, we use this nested MITM technique for synthesizing Tdepth optimal circuits. This time, we introduce some special class of unitaries, special set of unitaries, basically the product of RP terms such that the Tdepth is 1. So if and only if these RPs, the sequence of RPs, they satisfy some condition, then only it will belong to this set. And we show that the cardinality of this set is at most n factorial times 2 to the power 3n. This n is like the number of qubits. So in the nested MITM technique, again, the input is unitary, this test depth, and this C, which is the level of testing. And we have to output a circuit such that if the T depth is at most D, or we return no. Now, I'll not go into the detail of the algorithm due to time constraint, but it is nicely described in our paper. But what is important for this algorithm is this result. Suppose Si is the set of all unitaries which is implemented in T depth I. Then there exists a circuit with T depth D1 plus D2 implementing U if and only if this intersection is non-zero. That is, the set of unitaries with T depth D2 and this set S dagger D1 U, they have a non-empty intersection. And this is the comparison of the complexity of our algorithm with the previous best given by Amy, Maslow, Moshka, and Rotaylor. So we see like both the algorithms have dependence on the T depth in the exponent. But where it differs is in the base. So in our case, the base is the special set of unitaries which has this cardinality n factorial 2 to the power 3n. For AMMR, the base is the set of Clifford plus T circuits with T depth 1. And this has cardinality 2 to the power kn squared. This sort of introduces a significant difference in the complexity between these two algorithms. For example, if you want to generate this base set only, so this is the comparison between the generation time and the cardinality of these sets. For example, in our case, for 2 qubits, the cardinality of this set is 122, can be generated in time 0.014 second. For AMMR, the cardinality is 11,520, generation time 1 second. For 3 qubits, the cardinality is 2,282. In our case, with generation time roughly about 2 seconds. For AMMR, the cardinality is more than 92 million, and generation time is approximately 4 days. And they couldn't generate the 4 qubit unitary, so I've left the space blank. For our case, the 4 qubit base set can be generated in roughly 18 minutes. And this is sufficient to at least synthesize all T depth ones, synthesize any T depth 1 circuit. So now to further improve upon the complexity, we have designed some heuristic algorithms. First, I'll describe a polynomial complexity algorithm for Tcount. So the input is the channel representation of U. I'm taking the channel representation because it can be efficiently calculated from U. So now the output is a sequence of RPs and C0, and this is sufficient to this information is sufficient to construct the complete circuit. Now we can write this channel representation of U in this equivalent form as the product of RPJ hat inverse times the U hat is equal to the channel representation of some Clifford. So now the intuition is, instead of searching for product of RP, search for RP inverses such that this condition is satisfied. So what we do, we build again a number of trees. This time U hat is in the root, and then we prune the tree in order to reduce the complexity. For that, we introduce some divide and select rules. So we at each level, we group the nodes according to some properties or parameters of the unitaries, and then we select the group with the minimum cardinality. So we have studied 2 properties, the change in STE and Hamming weight. Now, just remember, I told before that the STE of a unitary when multiplied by a RP can change by at most 1. It can increase by 1, decrease by 1, or remain unchanged. So here Hamming weight is the number of non-zero entries in a matrix. So we have designed 3 divide and select rules. In the first case, we divide the unitaries into 2 sets. One in where the SD increased by 1, and in the second where the SD decreased by 1. If it remains unchanged, we say it is undetermined, and we place those unitaries in both the sets. Then we select the set with the minimum cardinality such that SDE is at most M dash. I'll tell you later why this at most M dash criteria comes. In the second rule, we first divide the unitaries according to the change in SDE and Hamming weight. If the Hamming weight remains unchanged, we divide according to the change in SDE. If the SDE remains unchanged, we place those unitaries in all sets. The selection criteria remains same. In the third rule, this is the finest subdivision we have had. If the change remains if the change is unchanged, I mean, if the delta ham or delta SDE, like the Hamming weight or SD remains unchanged, we place them in separate groups. The selection criteria again remains unchanged. So this is our algorithm. Now, as I said that the SDE, each time this RP is multiplied. Now this RP means one T count, right? One T count circuit. So each time it is multiplied, the SDE can change by 1. So we cannot have the T count of any unitary which is less than the SDE of its channel representation. So first we test whether the T count is at most the SDE. So for this, we multiply each unitary at level I-1 by RP inverse, and then we note the change in SDE and Hamming weight. And if the SDE of any product is 0, we know we have reached the Clifford, we stop and we return the path, which is the unitaries in the edges. Else we apply a divide and select rule with m dash is equal to m minus I. Now this m minus I means this is like the number of levels which are remaining in the tree. That is like the number of unitaries whose SDE can reach to 0 within the next m minus I steps. We only take those unitaries and not the rest. And the selected nodes become parents for the next level. If we do not find any decomposition here, then we again test for the next m and so on. So basically this 2.1 step, these iterations, they correspond to building one tree. So a tree which has this U hat in the root, then we multiply by RP inverse. So this edge means multiply by RP inverse. This is the product unitary or in the child node. Okay, now we divide and select. So we divided and selected these two nodes. We again multiply this by RP inverse. Again, we do a division and select. Then again multiply by RP inverse. Now this time we see that we have a Clifford in one of the nodes. So we stop and then we take the set of unitaries, the set of RP units, like these are unitaries in the edges, along the edges. And we say that U is equal to product of these RPs times this Clifford up to some global phase. Our conjecture is the set of nodes selected by the divide and select rule, they always include the correct nodes. These are the nodes that occur in a T-count optimal decomposition of the unitary, and the cardinality is at most polynomial in capital N. And this implies that the complexity of our algorithm, both space and time complexity, is polynomial in capital N and the T-count of U. So we have implemented some standard unitaries and some random unitaries. So we compare our result with the result by DiMatteo and Moshka, because this was the best before our work. And this is a parallel algorithm, which uses 4096 scores. So these are the unitaries we implemented: Toffoli, Fredkin, Paris, quantum or negated Toffoli, adder, U1 and U2. So U1 is one unitary which we obtained from this paper by Amy, Mashlov, and Moshka. This is a resynthesis algorithm, and they resynthesized a circuit with T-count with a number of T-gates 12. So we obtained the optimal T-count for all of them. For U1, we obtained a T-count which is less than that obtained by Amy, Mashlov, and Moshka. Our time is much less than the time of DiMatteo and Moshka. For example, this full adder, we can synthesize the circuit in roughly 7 minutes, and they take 12.5 hours. We use only one core, while DiMatteo, Moshka, they use 4096 cores. So we have synthesized some random unitaries as well. These are sets of 2, 3, and 4 qubit unitaries. And this number of T-gates means like we generated these circuits with at most so many T-gates. We obtained the unitary and then we put this unit, and these unitaries became input to our algorithm. And we saw that the output of our algorithm has a reduced T-count compared to the input. Number of nodes means the number of average number of nodes accumulated in the trees. This shows that the size of the tree remains bounded. That means the complexity remains bounded. And this is the average time taken for the synthesis. Now, of course, we couldn't verify whether all the circuits we obtained were optimal, simply because there is no efficient algorithm apart from our work that can verify our results. Okay, so but since in most cases, in all cases we obtained a reduced T count or reduced number of T gates, so it is a good indication that our heuristics might be correct for most cases. Now I'll describe a quasi-polynomial complexity algorithm for synthesizing T-depth optimal circuits. Okay, here again, as before, we obtained a sequence of RP units and the channel representation of C0. such that the Tdepth is at most such that the Tdepth is optimal. Now we can club these RP units if they satisfy certain criteria, such that we form these VJs which belong to this special set of unitaries that I described before. That like each of these unitary has Tdepth 1, and we can write this U hat in this way: the product of VJ inverse times U hat is equal to C0 hat. So now our intuition is simply search for this Tdepth 1 VJ inverse operators, such that this condition is satisfied. Again, we build a number of trees with U hat in the root, and we prune the tree. This time, we have two kinds of division. At the first level, in the first kind of division, at each level, we group the nodes into hypernodes according to path Tcount. Then within each hypernode, we group the nodes according to some properties or parameters. And we select according to some criteria. The properties are SDE and change in Hamming weight. Now, let me describe what is a hypernode and which is a path Tcount. So suppose this is a tree, and this is the root. And suppose this is another node in this tree, and each of these edges are obtained by multiplying by some V1 inverse. Then the path Tcount is the summation of the number of RP units in this VIs. Okay. Now, according to this path Tcount, we can group the nodes into hypernodes at each level. For example, if these are the nodes which are obtained by multiplying by all these VI units which have number of RP units 1, and these are obtained by multiplying VJ units which have number of RP units 2. Then in division 2, in each hypernode, we group the nodes according to their SDE and the change in Hamming weight with respect to the parent. Selection criteria is within each hypernode, we select the set with minimum cardinality such that the SDE is at most D dash. Again, the intuition is same. We take only those unitaries whose SDE has the potential to reach to 0. Now, I'll not describe the complete algorithm in detail. It can be found, like we have a nice description in our paper. Due to time constraint, I'll not go into so much detail. So here, the depth cannot be less than SDE of U hat by n or the Tcount of U by n. So we start with that. Again, we built so many trees with depth at most D. And if we reach the Clifford, we return the path, or we build a deeper tree. So this step looks as follows. So this is the unitary. We again multiply by V inverse and divide into hypernodes. Then we select some nodes in each hypernode. We again multiply by V inverse and divide into hypernodes. This time we see we already reached a Clifford. So we return the path, that is this unitaries on the edges. So U is the product of V1, V2, and C0 up to some global phase. And this unitary has Tdepth 2. And our conjecture in this case is cardinality of the node selected within any hypernode is bounded by poly n, and the nodes selected give at least one Tdepth optimal decomposition. Thus, both the space and time complexity is polynomial in log n factorial capital N and the Tdepth of U. Now, this is a comparison of our results with AMMR 13. They couldn't optimally synthesize any 3-qubit unitaries. We could optimally synthesize these 3-qubit unitaries. The depth obtained is 3. Since these are 3-qubit unitaries with Tcount 7, so this is the optimal result. And we could we could synthesize these optimal circuits in roughly less than 30 minutes. And we can see like all these depths are less than, some of these unitaries have less depth than that obtained by AMMR. Again, we synthesize some random 2 qubits and 3 qubit unitaries with maximum depth up to 20 and 7 respectively. And these are the average time taken and the maximum number of nodes accumulated in the tree. And we see like the tree doesn't blow up a lot. Again, we couldn't verify whether this is optimal, but since we get less Tdepth, so maybe it's a good indication that our conjectures are true in most cases. So to summarize my talk, we studied channel representation of unitaries. We analyzed these matrices, which helped us design more efficient algorithms for multiplication, inverse, etc., using integer arithmetic, and it also helped build the intuition for our heuristic algorithms. We also gave provable synthesis algorithms for Tcount and Tdepth optimal circuits. We introduced the nested meet-in-the-middle technique, which gave us a provable exponential complexity for Tcount, and it significantly improved the complexity for Tdepth. It also gives us a space-time trade-off for these kind of techniques. We designed heuristic synthesis algorithms, a polynomial complexity algorithm for synthesizing Tcount optimal circuits, and a quasi-polynomial complexity algorithm for synthesizing Tdepth optimal circuits. Thank you.